Hello everyone, welcome to the Unit 3 full syllabus revision with very recent question paper examples. So this is going to be a very advanced lecture. If you want a little less advanced and a more basic revision video, you can watch the last minute revision video for Unit 3 and the video link is given in the description. For your exam, there should be 3 resources that you should refer to for preparation. One is this video, which will cover the most recent papers from 2025 to 2023, and the basic video that will cover in general concepts like taking readings with micrometer screw gauge and vernier calipers. And there is an extremely detailed Unit 3 notes which comes with a free experiment sheet. And this includes communication with Pearson with some of the most complicated concepts that students are most confused with. And the download link is given in the description. So these 3 materials will be extremely useful for your exam. I repeat, one is this video, second would be the last minute revision video that I posted last year, and the experiment sheet including the detailed Unit 3 notes. Let's get started. The first question is from Jan 25, question 1. A student investigated how the acceleration of a toy car on a ramp depends on the angle theta of the ramp. She placed a light gate connected to a data logger near the bottom of the ramp. As the toy car passes through the light gate, the longest part of the toy interrupted the light beam. The data logger recorded the time t taken for the toy car to pass through the light gate. Always remember, light gate measures the time of interruption. Okay, and you can use the time to calculate the instantaneous velocity. So first question says, the student measured the length L of the toy car using digital calipers. Determine the percentage uncertainty in the measurement of L. So when you get a question like this, the very first thing that you need to identify is the resolution of the instrument. So it says 75.6 millimeter. So the resolution should be 0.1 millimeter. This aligns with this and this aligns with this part. So the resolution is 0.1 millimeter. Now, if the resolution is 0.1 millimeter, always remember for a single reading, uncertainty is resolution divided by 2. So 0.1 divided by 2, 0.1 by 2 gives you 0.05. And generally what we do is give a plus minus sign in front of uncertainty value. 0.05 units says the same, millimeter. And the question asks you to calculate the percentage uncertainty. Always remember the equation for percentage uncertainty is equal to uncertainty, which is 0.05 divided by measured value, that is 75.6 times 100%, which gives you, so the percentage uncertainty equals to 0.066%. And generally what I suggest my students is always give your percentage uncertainty to 2 significant figures, and which matches perfectly with the mark scheme value as well. Now, the second part of the question says, determine a mean value of t. Always remember, when you are calculating a mean value, the significant figure has to be consistent with the number of SF in the data set. So you can see all of these values are in 3SF, so your value must be in 3SF as well. So all you do is 44.7 plus 44.6 plus 44.9, 45.2 plus 44.5 divided by 1, 2, 3, 4, 5, which gives you, so the value I get is 44.78, but that is in 4SF. Like I just said, mean value has to be consistent with the number of SF in the data set. So T average or mean equals to round it off to 3SF, which gives you 44.8, which matches perfectly with the mark scheme as well. Now, the second part of B says determine the percentage uncertainty in the mean value of t. There are two ways of calculating the percentage uncertainty. One is using the instrument's resolution. The other one is from the data set. When a data set is given, uncertainty is always max minus mean divided by, max minus mean divided by 2. So you look for the maximum value. So the maximum value is 45.2 minus the mean value is 44.5. Max minus mean divided by 2 gets you 45.2 minus 44.5 divided by 2 gets you 0.35. And generally, the way I write my uncertainty is plus minus 0.35. And always remember, percentage uncertainty, equation for percentage uncertainty, regardless remains the same, whether it's for an instrument or a data set. So it's always uncertainty divided by measured value. And the average measured value in this case is 44.8 times 100%. And the value that you get is 0.78. And I give my percentage uncertainty to 2SF percent, which also matches with the mark scheme perfectly. The next question is from October 24, question 2. A student was given a sealed box that contained some electrical components. The sealed box could contain a diode, resistor, filament bulb, or a combination of any of these components. The student could not see the component inside the sealed box. Two terminals, X and Y on the sealed box, enabled the student to connect the component to a 6-volt power supply and a fixed resistor R. The student investigated the current potential difference characteristics of the sealed box. Complete the diagram to show the circuit the student could use for the investigation. So the investigation is to change current and potential difference and plot a graph. And the shape of the graph would determine whether it's a diode, a resistor, a filament bulb, etc. Right? So you have to vary the current and potential difference. And I was a bit surprised to see in this year the component they used to vary was a variable resistor. So this was the diagram for this year. So they used a variable resistor, but I have to show you something. A very similar concept came in the same year, October 24, but not of Unit 3. A Unit 2 question went like this. Check this out. This is question 14 of October 24, Unit 2. Draw a circuit diagram the student could use for this investigation. And the investigation was to change the current and potential difference. But this is what they had given. So this I found a bit inconsistent and a bit confusing as well, because generally you have to use a potential divider as an A-level student, not a variable resistor. And you might be wondering, is the same thing? It serves the purpose, right? So why can't we just use a variable resistor instead? What we have been doing since our IGCSEs. So I made a small comparison of the two circuits. Circuit 1 uses a potential divider and circuit 2 uses a variable resistor. The difference is in circuit 1, you get a full range of values of PD, but in circuit 2, you get a small range of values. You don't get any values near 0 volt or neither any values near the maximum PD, right, or the EMF. Whereas in circuit 1, you can change the PD from 0 volt to the maximum voltage, as in the EMF of the power supply. So this gives you a wider range of values, which makes your line of best fit or curve of best fit more accurate. So this is why for A-level physics, more appropriate instrument would be a potential divider rather than a variable resistor. The next question says, the student was told that the seal box contained a diode. Explain why the resistor is needed in the circuit. So let me show you the circuit one more time. This was our circuit, this one. So you might be wondering, I can just change the resistance of the variable resistor that would change the current and the potential difference, right? So why would I need a resistor like this here? What is the purpose of this resistor? A resistor is needed to prevent a short circuit, because when you lower the resistance to such a small value, an unimpeded amount of current can start flowing, which can cause a short circuit. So the resistor limits the amount of current that can flow in the circuit to prevent a short circuit, because this is only applicable when you are using a diode, because the moment the diode starts conducting, that is, it is in the forward bias, its resistance drops significantly. So let's look at the marking points. What does the mark scheme say? A fixed resistor is needed to limit the maximum current in the circuit, or the fixed resistor is needed to prevent a short circuit, because in forward bias the diode has a low resistance and the current in the circuit will be very high. Yeah. So the next concept is associated with health and safety. So we'll look at two examples, one from Jan 25, the other one from Jan 24. Jan 25 says, concrete is often used to make supporting beams in buildings. Strands of a material can be added to the concrete mix to produce fiber reinforced concrete. A student had some small beams made of fiber reinforced concrete. Each beam was the same size. He placed a beam across two supports as shown. Identify a health and safety issue with the method and how the issue may be dealt with. Okay. What's going on here is you have to place loads over here and you have to check the force at which the beam breaks. And when it breaks, fragments of the concrete can uh, hit your eye. So you have to wear protective eyewear, number one. The other one is the mass after breaking can land on your feet. So you have to move your feet away from the experiment. So let's see the points. Mass or the beam could fall and injure the feet or legs or hands. Place a box or cushion underneath the experiment, right? Or the other approach is the beam could shatter and pieces enter the eye. So wear goggles to protect the eyes, or you can just combine this and say wear protective eyewear. Now let's move on to the question for Jan 24. A student uses a laser and a screen to determine the diameter of hair. The apparatus was arranged as shown. Identify a health and safety issue by using a laser. They have specified what are the health and safety issues associated with using a laser. So if it's a very strong laser, pointing it directly in your eyes can cause eye damage. So you have to wear um, dark lens sunglasses to protect your eyes. So the dark lens part is very important to mention when you're dealing with lasers. But when it comes to protective eyewear for the first question of Jan 25, you don't have to mention anything about dark lens. And that would be a problem actually. If you wear dark lens, you won't be able to see the values properly. But when you're dealing with a laser, you have to mention dark lens laser. Check this out. Laser light may cause damage or irritation to the eye. Wear dark lens safety glasses. Yeah. Let's move on to the next question. The next concept is repeatability. Whether it's a good idea to repeat the experiment. Right? So the first question we'll be looking at is of May 24, question 1b. A student investigated the force needed to break a rubber band. The student investigated how breaking force of the rubber band changed at low temperatures. The student placed 5 identical rubber bands in a freezer at minus 10 degrees Celsius. The student removed one rubber band from the freezer and determined the breaking force. He repeated this for the other rubber bands. Explain why it is appropriate to repeat the measurement. So they're not just asking you whether it's a good idea, they're asking you why is it a good idea. So let's look at the points. Repeating the measurement reduces the effect of random error caused by variations in the temperature of the rubber bands, because the temperature is not going to stay constant, it is going to change a little bit. So if you keep on repeating, this will reduce the effects of random error, random variations in your measurements. For Jan 24, question 2b says, a student investigated the efficiency of an electric motor using the apparatus shown. Explain why repeat measurements are appropriate for this measurement. The format is going to remain the same. Let's see, what does the marking say? Random error will cause variations or anomalies in the values. Repeat readings allows a mean to be calculated to give a more accurate value. So they have added an extra point here. Um, a mean value will be more, the mean value will be more accurate if you repeat your readings. Okay, so the next concept is how to take accurate single value. The first example would be from October 24. The student filled the tall beaker with water. He used a meter rule to measure the depth h1 of the water. Describe an accurate method to determine a single value of h1. And you have a similar concept in May 24, question 3. A student determined the speed of ultrasound in air using the apparatus shown. The student added water to the transparent tube to change the length S of the air column. Describe a method to determine a single value of S as accurately as possible. Right, so when you look at the two values, let's say H1 or S, both look vertical, right? So your meter rule has to be vertical. And how do you ensure your meter rule is vertical? Using a set square. And also, you can clamp the meter rule. So these 2 points are optional points. You choose one or the other. So if you say clamp the meter rule to a fixed position and use a set square to ensure meter rule is vertical, you are not getting two separate marks. This is only one mark. Always remember this. Then, if you are taking readings with a meter rule, you have to take readings at eye level. So this used to be a very common point, but the mark scheme has evolved. Now you don't write take readings at eye level. What you write is take readings perpendicular to the scale, right? So let's look at the marking points. Ensure meter rule is vertical using a set square or clamp the meter rule in position. Like I said, these are optional points. Place the meter rule close to the beaker. You know why? This would reduce parallax error. The farther away you take the meter rule from the beaker or the tube, the greater will be your parallax error. So if a question were to ask you, why do you have to keep the meter rule close? To reduce parallax error. And then read perpendicular to the scale, and this point was previously known as take readings at eye level. The next concept is very important, how to draw conclusions from your calculations. This is example from October 24, question 1c. The student determined the viscosity of the liquid as 0.74 Pascal second. Always remember the unit of viscosity is Pascal second with a percentage uncertainty of 6%. The viscosity of castor oil is 0.65 Pascal second. The question is asking you to deduce whether the liquid could be castor oil. So in these type of questions, my personal favorite method is always to calculate the percentage difference. So you need to find out how different your value, your experimental or calculated value is from the reference value that is of castor oil, right? So percentage difference equals to 0.72 minus 0.65. Since we need to check how far off my value is from castor oil, you divide by the value of castor oil, 0.65 times 100%, and the value that you get is 11%. Step 1 is done. Next step is to compare the percentage difference with percentage uncertainty. Always remember, if the percentage difference is smaller than percentage uncertainty, then and only then you can conclude it is acceptable, it is suitable, or in this case, it is made of castor oil. But here, since percentage difference is greater than percentage uncertainty, it is not castor oil. I repeat, always remember for acceptability, suitability type of questions like this, always compare percentage difference with percentage uncertainty. And for the value to be suitable, acceptable, or valid, the percentage difference has to be smaller than percentage uncertainty. Next up, we have measuring technique. And the question is from Jan 24, question 1. A student had a stack of 500 sheets of paper. He measured the dimensions shown. The student used the vernier calipers to measure the thickness Y of the stack of paper. Explain one technique he should use to determine an accurate value for Y. So, how do you ensure accuracy? You ensure accuracy by minimizing the two errors. And what are the two types of errors you have? One is random error and one is systematic error. If you can reduce these two types of errors, you are moving towards your accurate value. So it's a 2-mark question. You either talk about systematic error, how to eliminate systematic error, or you talk about the way you can minimize the effects of random error. So this is the answer. Check for zero error, correct the value to eliminate systematic error, or so these go in pairs. The 2 points are for systematic error and the 2 points are for random error. Repeat the measurements in different places and calculate a mean to reduce the effects of random error. Also remember, you can eliminate systematic error, but you cannot ever eliminate random error. You can only minimize the effects of random error. Next up, the question says, a student had a stack of 500 sheets of paper. He measured the dimensions shown. Explain why making measurements on the whole stack of paper is better than making measurements on a single sheet of paper. For this, I want you all to recall the equation for percentage uncertainty, which is uncertainty divided by measured value times 100%. So the instrument that you are using remains the same, whether you are making measurements on one single sheet of paper or 500 sheets of paper, right? So the resolution of the instrument remains the same. In turn, the uncertainty remains the same. But when you are taking measurements of 500 sheets of paper, the measured value increases. And guess what? The moment the measured value increases, the percentage uncertainty decreases. And this is what we always seek to reduce percentage uncertainty in our measured values. So let's look at the mark scale. Check this out. The measurements of the thickness and mass are larger, so the percentage uncertainty is smaller. For the same uncertainty at times, the uncertainty remains the same is actually a marking point if it were a 3-mark question. Next question says, a student investigated the inverse square law for light. So we'll be focusing very much on this specific question. We'll cover all the points, all the parts of this question. The student investigated inverse square law for light using the apparatus shown. The student used a meter rule to measure the distance d between the filament of the bulb and the sensor of the light meter. The reading on the light meter is the intensity I of the light. The value that you see on the screen is actually the intensity of light. Fine. Explain two sources of error. Explain how two sources of error can be reduced in this investigation. So what are the two sources of error? In any experiment involving light, where you have to measure the intensity of light, one big source of uncertainty is always the presence of background light. Okay, so I think this will be there in the mark scheme as well. So you need to eliminate background light. And how do you do that? By performing the experiment in a dark room. Let's see if this point is there. Yep, the very first point. Background light will affect the readings on the light meter, so conduct the investigation in a dark room. Then, this is a 4-mark question, so 2 marks won't cut it. The next 2 points would be, there will be parallax error when measuring the D. So use a set square between the ruler and the sensor. Let me show you what they mean. So let's say if this is your ruler, the ruler might not be perfectly horizontal, right? It can make an angle like this or this. So that will create parallax error. So for that, you can use a set square to ensure that the ruler is perfectly horizontal. Plus, a set square will allow you to identify from which point you start taking the measurements. So you can place your set square over here because you want to take readings from the filament, and this is your sensor, and then you place the meter rule in between these 2 points. This is where you place your meter rule. The next concept is choosing a measuring instrument, and this question is from May 23. A student investigated the diffraction of electrons using an electron beam tube as shown. The student used vernier calipers to measure the diameter of the rings on the curved screen. Give 2 reasons why vernier calipers are more appropriate for these measurements than a transparent ruler. So you see, this is a curved screen and there are rings that you have to find the diameter of. So how exactly do you take readings from a curved screen with a meter rule? There will be parallax error. The meter rule will not line up perfectly with the curved screen, right? So that's why the tips of the vernier caliper will align perfectly on the screen. This is one point. The other point is vernier caliper has a higher resolution, and I see so many students all around the world getting confused with higher resolution and smaller resolution. Because in the mark scheme, sometimes they say smaller resolution. For example, this year they said the vernier caliper has a smaller resolution. But in other papers, more recent papers, they say vernier caliper has a higher resolution than a meter rule. So what's the difference? Always remember, when you talk about resolution, there is a quantitative approach and a qualitative approach. A smaller value of resolution means the instrument has a higher resolution. So in this context, vernier caliper has a smaller value of resolution. Therefore, it means a vernier caliper has a higher resolution. I talked about this in great details in the other basic Unit 3 last minute revision tip video. You can watch that. I think this will be very important if you still have some confusions. So for this one, let's look at the marking points. Vernier calipers have a smaller resolution. Like I just said, vernier calipers have a smaller resolution means it has a smaller value of resolution, which means it has a higher resolution. Vernier calipers can measure without parallax error. Why? Because the tips of the vernier caliper are easier to align with the rings as the surface is curved. So for curved surfaces, if you have to take readings from curved surfaces, meter rule is not going to be useful. You have to use a vernier caliper. So the next question is not entirely a unique Unit 3 question. This is more aligned with Unit 2. But one of my students requested me to include this question in the video, and I found this extremely difficult and intellectually challenging. So that's why I've included this. This is from 21, and you'll see no other question is from 21 year or year 21. Now, a student investigated the reflection of microwaves from a metal plate and a glass plate. The metal plate reflects microwaves and the glass plate partially reflects the microwave. So this is what's going on here. So this is the transmitter. So microwaves partially get reflected from here, travels all the way through and gets reflected from here. Oh, I think it's better if I do it this way. One is from here partially, and the other one gets reflected from behind, like this. So these two rays or waves, this is what we are concerned with. And these two waves superpose at the receiver. And there is a path difference. Can you guess what's the path difference? What is the extra path that this wave has traveled? There is d in this way and d in the other way. So the path difference is equal to 2d. So the extra path that a wave travels is always referred to as the path difference or difference in path lengths, right? Now, the student recorded the values of d when the receiver showed a maximum value of intensity. He recorded d for a sequence of 5 maxima. Fine. And let me remind you, when does maxima occur? Maxima, they have specified maxima, not a minima, right? So a maxima occurs when the path difference is a whole number of wavelengths, right? Maxima occurs when a path difference is a whole number of wavelengths. So path difference should be n lambda. And here you have a path difference of, sorry, you have a path difference of 2d should be equal to n lambda. So this distance is actually lambda by 2. For different maxima, this distance is always equal to, bring 2 on the other side, lambda by 2. Okay, and this distance is the difference between the maxima, right? So you find out this difference between the maxima, this difference, and finally this difference. And the value that you get, the mean value, of course. So this is 1, 2, 3, 4. You have 4 values, and you find out the mean distance equals. So the mean of all the differences is 1.375. 1.375. So this d is 1.375. And the question asks you to find out the wavelength. So make lambda the subject of the equation. Lambda should be equal to twice d. So 1.375 times 2 gives you times 2 gives you 2.75, or rounded off to 2ff, you get 2.8 centimeter, which matches with the mark scheme as well. Next topic is very important. You have graphs. So this is also from January 4, question 4. The relationship between I and D is given by I equals K by D squared. So I hope you all remember from your Unit 2 intensity lecture that intensity equals power divided by, if it's from a point source, it's always 4 pi D squared, right? So the power is constant, 4 pi is constant, so I is proportional to 1 by D squared. So this is the basic concept behind this question. So the question says, explain why a graph of I against 1 by D squared should be a straight line to the origin. So you isolate K from here, or 1 by D squared. So I equals to K times 1 by D squared, which is in the form Y equals to mx. I on the y-axis and 1 by D squared on the x-axis gives you a gradient equal to K, which is a constant. Because question says K is a constant. So the gradient is constant, plus there are no y-intercept. Now let's move on to the most important part. That is plotting a graph. So the question said, plot a graph of I on the y-axis and 1 by d square on the x-axis on the grid. Step 1 is to label the axis with units. This is your number 1 responsibility. So for y-axis, you have intensity, and the unit of intensity is watt per meter square. And for x-axis, it's 1 by d square. So d square is meter square. So 1 by d square is per meter square. Next up, you have the scaling part. Scaling is very, very, very important, guys. And before scaling, the increment has to be after every 10 square. So you see where I have placed the increments after every 10 small square. Always, there is no exception with this. And I see so many students still struggling with this idea. What will be the value of the increments? You only have 3 options. It's either 1, 2, 5, or their multiples of 10. Higher multiples or lower multiples. For example, it could be 0.1, 0.2, or 0.5. What I mean is these values. This can either be 1, 2, or 5. This value, right? Or this was the smaller increment. The higher increment would be 10, 20, or 50. What I mean is over here you either place 10, either 20 or 50. What you can never do is place 40 or 30 here. That would be construed as awkward scales, and that is not going to get you any marks, and you'll be penalized 3 marks actually. Next. And also remember, for the scaling part, your graph should cover more than 50% on both axes. And this is what your plotting points look like. Always remember, the graph has to be balanced with roughly equal number of points above and below the line of best fit. So let's count. This point lies on the best fit. This point somewhat also lies on the best fit. And finally this one as well. So you have 1 point above and 1 point below the line of best fit. So this is what you have to ensure. And in the mark scheme, they did not pass this line through the origin. But when I drew this, I made it pass through the origin because the equation satisfies this concept. Plus, when I tried to pass it through the origin, it was not a biased graph, it was a balanced graph. So if your concept says that it should go to the origin, you can definitely pass it to the origin. And this will give you an upper hand with the next part of the question, that is the gradient. Once the graph passes to the origin, one coordinate is already 0, 0. So you have to consider only one other plotting point. Not plotting point, a point that lies perfectly on the graph. For this specific scenario, this is the point. And you might be wondering, why did I choose this point? Why not, let's say, this point or this point? Because while calculating the gradient, you have to ensure that this is a large triangle. So the value that I get is this is 900, 910, 20, 30, and 40. So this is 940, and this is 60. So the gradient is always change in y-axis by change in x-axis. So this is the upper hand that I got by making the graph pass through the origin. So this is 940 minus 0 divided by, that is the change in y-axis, and this will be the change in x-axis, which is 60 minus 0. So you only need to deal with one plotting point if your graph starts to the origin, and the value that you get for the gradient is 940 by 60, which is 15.7, which perfectly matches with the bar scheme. Of course, you have to give the unit as well. Unit would be what? I'll tell you why. Because intensity equals to power by area. And for area, you had 1 by 4 pi d square, right? So when you look at this and compare it with y equals to mx, the gradient should correspond to power, right? And that's why the unit would be 1. Thanks for watching, and that's more or less all you need to know about graphs, and good luck with your exam.